Hello everyone, this is Professor Robert Solis. Welcome to this video lesson. This is going to show you some examples of how to take a circuit and determine what its expression is, or take an expression and then turn it into a digital circuit. So let's take a look at example number 1. It says, what is the expression of the circuit below? So here we are given a circuit. It looks like we've got an inverter, 2 AND gates, an OR gate, and then another AND gate. So the input signals are P and Q, and then here's the output. So what we're going to first do, step 1 would be to create a truth table. And we have the input P, Q, and output. So what you would first want to do is to count in binary 0, 1, 1, 0, and then 1, 1. Let me make these guys a little bit bigger here. A little taller, I should say. So you have your input signals, and once you have the input signal, then we could step by step go through these to find out what the output is supposed to be. Okay, so let's assume that, let me actually choose a different layer really fast here so that I can just simply erase this quickly. Let's see here, input 0 and Q is 0. So P is 0, Q is 0. Well, 0 going through an inverter is binary 1. Okay, so 0 and 1 is going to be 0 because false and anything is false. This is false and this is false. And so false and false is false. False or false is false. So there's a 0 going into here. It looks like this 0 goes over here to the output. False and false is false. So that's what this is. Let me go ahead and erase these, and we'll try it again. For the input P being 0 and Q is 1. Okay, so this will be 0, this will be 1. Alright, 1 is inverted, so that's going to be 0. And false is going to be false. Looks like the false propagates over here, and this is true, but doesn't matter because false and anything is false. We have both of those false or false going through an OR gate, so that's going to be 0, and we know that 0 and anything, or false and anything, is going to be false. So the output based on this input is false. Okay. Let's try the next one. Looks like P is true, or 1. Q is going to be false, or 0. Alright, 0 inverted is going to be 1. 1 and 1 are true, and true is true. I have this one going over here. This 0 propagates over here, but that means going through an AND gate, false and anything is going to be false. And then I have true going through this OR gate, so that's going to be true. I have 0 going all the way over here, true and anything. Well, I should say false and anything is false, so this is also going to be false. Next, we have both of the inputs are true, so let's see what happens here. So if I put a 1 over here and a 1 over here, that's going to turn into a 0 after it goes through the inverter. False and anything is false. How about over here? So it looks like I've got 1 over here, I've got 1 over here. True and true is true. True or anything is true. So there's a 1 going in here. It looks like there's a 1 going all the way over here. True and true is equal to true. Alright, so this is our truth table. And let me do this. Let me just put the word truth table right here. Table. So this is our truth table. Oh, didn't spell that right. There we go. For this particular circuit. Now, if I wanted to take this and see if I could reduce this circuit, I would do the following. So first of all, I'd have to determine which one of these outputs is true. It looks like I only have one of them that is true, and the only time that that's going to be true is when the signal P is true, so we'll just put P over here, and when the signal Q is true. So like this, right? All other times it looks like the output is false. So it looks like we say P and Q. Now in the engineer's notation, so I'll just say engineer's notation, let's see here. That looks like Enya. Engineer. I meant that to be an R, right? In the engineer's notation, we would just simply do this. We would say P dot R, which is P and Q. And logicians, or mathematical notation, so logician notation. You would say this, P, and it's an incomplete A. That symbol right there means and this is Q. Okay, so if I were to take this and convert that into a circuit, well, that's just simply an AND gate. So let me go over here and drag and drop an AND gate and prove that to you. Because if I were to take the signal P as one of my input, Q is the other input, the only time that the answer is going to be true is when P is true and Q is true, like this. If this is true and if this is true, then the output is true. For all other situations, the output is false, right? Because false and anything is false, false and anything is false, and of course if both of these are false, the answer is false. So really what we were able to do is take this entire circuit and reduce it into a simple AND gate, and that's going to basically replace all of this. Alright, so this is Professor Robert Solis. I hope this example was helpful, and I'm going to be working on some more examples for you to take a look at. Take care. See you next time.